Hi everyone, so welcome to my series on classical planning. This will be an introduction to the field of classical planning. We're going to be spending a lot of time in this domain. I think it's a very exciting one. It is so adjacently related to the idea of pathfinding, right? We're taking all of the concepts we know and love from heuristic search, from pathfinding, we're translating that across just to the idea of essentially harder problems, like real world problems. I want to solve a Rubik's Cube. I want to solve a sliding tile puzzle. I want to solve the word puzzle, right? Whatever it is, whatever real world situation you're going to be modeling and then being able to solve, classical planning is your first go-to situation. Now, we're going to talk essentially in terms of what we say simplifying assumptions, right, are important. Really what I like to think about instead is it's just these are important characteristics about the problem that actually enable us to solve it in the basic sense. In terms of the scale and the way we solve problems, really classical planning is our first go-to frontier, but this actually corresponds to essentially like the easiest version of problems. When we start adding harder characteristics of the task environment, fancy language to just say, when we start having things like probability or limited senses and things like that, we will have to go beyond classical planning to ideas that still very much draw heavy inspiration from the baseline ideas that we will be studying in this subject, in this field. Now, what is classical planning? I think up front, I just want to say, I think it's a fancy term that is intimidating to a lot of students. Classical planning is just, we're going to solve it with states, right? We're going to map states from your initial state to your goal state. You're going to do that by performing actions. We're just doing search, okay? So we need a way to formally model the environment. That's going to be the next video. We're going to use languages such as strips and PDDL. We're going to model the environment. We're going to take actions, which is just node expansions and branching. Ta-da, do a bunch of things. Search over that using our age-old heuristic search and things we've seen. Ta-da, we get to the goal state. That's classical planning. The important assumptions that are actually driving this, though, first is that it's essentially fully observable. Okay, so essentially in the problem, what that means is that we need to be able to see everything. So imagine you are like a global controller. You're able to see the whole grid you're solving. You're able to see the whole Rubik's Cube. You're able to see the whole maze that you're in, or whatever else it is, really. It is a bit limiting, but it's oftentimes, really this is kind of relating to the idea of senses. Just as a robot or whatever else, you kind of just assume that you have the full picture of the world around you, right? You're able to see everything. You're able to see all of the effects of your actions. You're allowed to essentially reason over the whole state space, all the possible locations you could get to. Now, when I say that you can get to a location, this just means that your actions are deterministic. In a deterministic world, what that means is just that when I take an action, when I decide to move forward, right, I move forward every single time. There is no probabilistic nature to the environment. It is deterministic. Everything I say, the robot executes correctly. It does what I tell it to do. Now, yes, that may not always be realistic, but all of these assumptions are, I think, still very reasonable. I relate to a wide range of real problems that we can also just like make simplifying assumptions. You know, hey, even if your robot only has like an 80% chance of actually rolling forward, maybe its tires break or whatever, I think it's very, very like realistic and reasonable, right, to still model the problem in this classical planning domain and worldview, solve it that way, and then, you know, we can do additional reasoning and problem checking and stuff in some like onboard later worldview, whatever else. But yeah, deterministic just means like when I tell you to do an action, it happens every time. This goes part and part, right, with the fully observable. I'm also seeing what the effects are. I know my exact location. I know my new location. Actions as well obviously don't have to be movement, right? In classical planning, we're representing any real world problem. So maybe it's spinning your cube. Maybe it's rotating your robot. Maybe it's doing whatever. Maybe it's sliding the tile to that location, so forth. Maybe it's like in a real world problem, you're like changing tires on a car. Maybe it's take off tire, something like that. when you say it, it happens. Now, yeah, the last one then is this idea of it's also a static environment. Just meaning that when I'm planning, like while I'm trying to reason over the world, come up with a solution, come up with a sequence of actions, things don't change, okay? So that is often also quite realistic, but of course, sometimes unrealistic. So an example like traffic or things like that. Of course, in the real road, things can change. But if you're in some autonomous robotic warehouse, right, and maybe you're controlling all of the robots, well, then you can kind of assume it's static, right? Things don't change. Boxes don't suddenly move on their own. Yeah, so when we're saying static environment, we just mean that essentially the only things that affect the world, right, to transition from one state to another is the actions we take. Nothing else changes. There is no dynamic environment. There aren't doors closing and opening. There aren't other robots and objects we didn't know whizzing about that weren't controlled by the actions that we are taking, or that are modeled in the problem, right? We could still have other robots modeled as something that we don't control, but at least we know where they are. Then we know the constraints, we know where they are at this location, so forth. While we're planning, we have that information available to us, and essentially after we plan as well, when we go to execute, things aren't also suddenly they haven't changed on us. So really, yeah, it's just saying that nothing changes in the environment except with the exception of the actions that we take. Now, what I do want to get across then is that essentially, as I said, all of this is really a fancy way of saying we're at some initial state, okay? We need to take some sequence of actions that who knows what it looks like, right? But we are just getting to some goal state as well, okay? What are we doing? Well, the things we're doing are actions. We are interacting with the world. We are taking operators, whatever else you want to call it within the language of classical planning. But this is similar to, again, kind of like search, right? This is your search problem. You look at the possible actions, the branching factor that you can do, and then from each of these, we define a new state, a new node. From there, you look at all the things, so forth. Sometimes you have different numbers of things that you can do, right? And so forth. And we're trying to find some version of the path that gets all the way to our goal. Of course, this is not easy. We've seen this in heuristic search. This will be the case in classical planning too. Essentially, finding optimal solutions in classical planning is going to be very difficult. Oftentimes, we even just deal with the idea of satisficing, finding a good enough plan, just something that gets me to the goal. So there's a whole bunch of cool algorithms we'll look at here. As I said, like in this initial state, the first thing we're going to deal with in the next video is that we have to model this, right? We're going to use things like strips or PDDL. These are languages, ways of formally describing a problem and essentially translating it to the idea of states. And we're going to be using facts and information, predicates, objects, things that we can reason about the world. We'll define operators, actions, we'll define things that we can do. And we'll define them in terms of essentially also like the preconditions, what needs to be true in order to do it, and then the effects, what happens, what changes in the environment as a result of me taking an action. Then you're also modeling around the transition function, like, okay, how does taking the action pick up, translate me from one state to another, so forth. Then we will solve this. We solve this using things such as heuristic search, things like the A* algorithm, okay? So we, of course, need some way to map our way through the state space, right? Taking individual paths in order to arrive eventually at the goal. Doing so blindly sometimes works, but most of the time definitely does not. So we do need the idea of heuristics, and that whole field, right, is really just hand in hand with these problems. This is how we model the problem formally and are able to actually computationally solve really difficult things. And yeah, so all of that was getting to the goal which we also modeled and defined at the beginning. So this is going to be my series on classical planning. This is really interesting, super applicable to the real world. Yes, we're not currently dealing with probability. We're not dealing with probabilistic actions. We're not dealing with time per se. You can model time in classical planning, but we're also not dealing with things like perhaps you don't actually know where you were dropped into the environment. Maybe your robot only has a few sensors available to it. Maybe it doesn't know where it actually ends up when it takes action. So that all of these like real world messy constraints does relate to other fields of study. Maybe we'll do things like machine learning, reinforcement learning. Maybe we'll do things like there's these model-free aspects, there's Markov decision processes and partially observable Markov decision processes, so MDPs and POMDPs. Those are the other fields of study. Future videos, future series, well in the future. But classical planning is super exciting, and please stick with me for the next video. Thanks.